content of 40%. That's going to markedly increase your alveolar PO2, and we can calculate that number. Let's say 40% times 760 minus 47, and we subtract the PCO2 divided by 0.8. Okay. We still have the same AA gradient, 50 millimeters of mercury, but if we start at 200 for your PaO2 and you have a 50 millimeter AA gradient, then the PaO2 increases to 150. Did y'all follow that? Okay. Any questions about gases, exchange of gases? How oxygen's carried, how it's unloaded? All right. Generally on this upcoming test, if there's an area where the class does poorly, it's in physiology, not dramatic, so much. Yeah.
Back to number 2 on the quiz. How sorry, excuse me. Arterial oxygen content decreases, right, for number
Yes.
2. Is that? Can you explain that one more time? Because there's less hemoglobin to pick it up, or
Right,
hemoglobin's
because
picking
the
it up?
oxygen content is equal to dissolved oxygen plus oxygen bound to hemoglobin. Okay? Now, the drop in hemoglobin is not going to impact the dissolved oxygen. Your PaO2 is going to be the same. Okay? But if you have less hemoglobin to carry oxygen, the amount of oxygen that's actually bound to hemoglobin is going to be different. You know, when your hemoglobin falls, your maximal oxygen carrying capacity, instead of being 15 grams times 1.34, your maximum oxygen carrying capacity is going to drop down to 12 grams times 1.34. And that's before multiplying time percent saturation. So if your hemoglobin concentration falls, then the ability to carry oxygen by the hemoglobin is going to drop by 3 grams. Doesn't affect your PaO2. Dissolved oxygen is the same. Anybody else? What they say, a word to the wise is sufficient. So that's sufficient. Let's do this now. Let's talk a little bit about lymphatics, and I'm going to do this for about 30 minutes. And then what I want to do is just look under the microscope at some lungs. I found it. All right. I want you to think of this as a capillary, a single capillary within a capillary bed. Okay, so this is a capillary, so that means that blood is being delivered by an artery, and it's being drained from the capillary into a vein. Of course, the vein is going to deliver that blood back up to the heart. Now, that capillary is lined by a simple squamous epithelium, what we call an endothelium. So let's draw in some endothelial cells. These endothelial cells are separated by a tiny gap called an intercellular cleft. So there are lots of little intercellular clefts between adjacent endothelial cells. And these intercellular clefts allow for filtration. This is your most common type of capillary that I've drawn, your continuous capillary. Okay, the endothelial cells are separated by tiny intercellular clefts that allow for filtration. Filtration represents extravasation of fluid, movement of fluid from the blood into the surrounding interstitial fluid under the influence of some force. So we can think of it as blood being pushed out through these intercellular clefts into the surrounding tissue fluid or interstitial fluid. So I've color-coded this to show both the arterial side here and the venous side of the capillary. Same thing is depicted here. This is the arterial side and this is the venous side of this particular capillary. What this slide shows here is that on each side there are two forces that influence filtration: hydrostatic pressure and oncotic pressure. Hydrostatic pressure and oncotic pressure. Now, to begin our discussion, we're going to ignore the venous side of the capillary bed. We're just going to focus on the arterial side. Hydrostatic pressure literally means the pressure created by water. And you know that the plasma within our bloodstream is mostly water. So we can refer to the blood pressure, the mean blood pressure within the capillary, as hydrostatic pressure. The mean pressure within a typical capillary is about 35 millimeters of mercury. And this pressure is generated within the capillary and tends to push fluid out. So it tends to cause extravasation of fluid from the bloodstream into the interstitial space. Now, if there was any buildup of pressure within the interstitial fluid, we would have to account for that in calculating the net hydrostatic pressure. In other words, if there was a buildup of fluid here in the interstitial such that it triggered generation of hydrostatic pressure, well, that hydrostatic pressure outside the bloodstream would then counter the hydrostatic pressure within. And so we'd have to subtract one from the other to determine the net hydrostatic pressure. Well, it turns out that interstitial fluid is constantly being mobilized. It's picked up by the lymphatic system and removed, such that, for all practical purposes, the hydrostatic pressure within the interstitial fluid is zero. So there's no opposing force in terms of hydrostatic pressure. If we were to calculate the net hydrostatic pressure along the arterial end of the capillary, it would simply be 35 minus 0. It's a positive number, meaning that this net pressure is pushing fluid out. Now, the second force that influences filtration is oncotic pressure. Oncotic pressure is simply osmotic pressure that's created by proteins. Most proteins within the bloodstream are synthesized by the liver, released into the bloodstream, and stay there. Why? Because these protein molecules, for the most part, are too big to pass through these intercellular clefts. Besides that, most have a negative charge. So they're not lipophilic. They can't cross through membranes like the endothelial cell membranes. So the proteins are trapped inside the bloodstream. Okay? I'm going to do a little flashback to AMP1. We have a beaker filled with water. We have some type of semi-permeable membrane that allows movement of water across. But the little holes in the semi-permeable membrane are too big to allow the movement of proteins. And then I dump protein into one side of the beaker. Well, those proteins, those solute particles, are going to create osmotic pressure. Again, when the osmotic pressure is created by protein, we call it oncotic pressure. And it's going to pull water from the side without the protein to the side where the solute concentration is higher. And so over time, we see a change in the level of water as a result of this oncotic pressure and the movement of water that it induces. Now, because most of the protein here is within the blood, it creates oncotic pressure to the tune of about 26 millimeters of mercury. This 26 millimeters of mercury, by the way, is it pushing fluid out or is it pulling fluid in from the interstitium? It's pulling fluid in from the interstitium. We can think of this capillary wall as being like this semi-permeable membrane. Now, there's a very tiny amount of protein in the interstitial fluid, so in calculating that oncotic pressure, we have to subtract that, but it's almost negligible, it's 1. So the net oncotic pressure pulling fluid back in is 25, but it's moving in the opposite direction from the net hydrostatic pressure. So to calculate the total filtration pressure or the net filtration pressure on the arterial side, I have to subtract that oncotic pressure from the hydrostatic pressure that is tending to push fluid out. So if I subtract the net oncotic pressure from the net hydrostatic pressure, I get a total net filtration pressure of 10. I get a positive number. So that means that at the arterial end, water, okay, which is the main component of plasma, is being filtered out. In fact, you should know that all capillary beds are sites of filtration. So water is being filtered out. Okay. What's the force that's pushing it out? It's the net filtration pressure, 10 millimeters of mercury. So we said filtration is the movement of water that's created by some force. Well, it's the net filtration pressure. All right, now let's move now to the venous side. We know that the hydrostatic pressure along the venous side of a capillary is going to be lower than the hydrostatic pressure at the arterial side. Why? Because as blood moves from point A to point B, there's got to be a pressure gradient. So it's got to be lower. The net hydrostatic pressure on the venous side is simply the venous pressure, which is 17 millimeters mercury, minus any hydrostatic pressure in the interstitial fluid. Well, there's none. So the net hydrostatic pressure on the venous side is simply 17 millimeters of mercury, tending to push fluid out. But again, as in the arterial side, on the venous side, there are two forces. We have to also account for the oncotic pressure. Because the protein creating oncotic pressure doesn't leave the bloodstream, the net oncotic pressure is the same as it was on the arterial side. It's 25. But this time, we're not subtracting 25 from 35, we're subtracting 25 from 17. That gives us a net filtration pressure on the venous side that's negative. it tells us it's drawing fluid in to the tune of -8 millimeters of mercury. So, from this graph, we can see that fluid is being extravasated, pushed out on the arterial side, and then pulled back in on the venous side. But because the net filtration pressure on the venous side is not the same, it's a smaller number than the positive net filtration pressure on the arterial side, what we can gather is that although some fluid returns on the venous side, there's some fluid that remains within the interstitium. If this number was -10, it would tell us that all the fluid that's extravasated is picked right back up. But that's not the case. There's more fluid leaving at the arterial end than returning to the bloodstream at the venous end. Okay? So this generates interstitial fluid. This causes a buildup in interstitial fluid within the scapulary bed. Yes?
You said that some of the fluid on the venous side is still left in where?
This space here, the interstitial space.
Okay.
What does interstitial space mean to you? Yeah.
Outside the capillary?
Outside, not only outside the capillaries, but outside the cells of the tissue. Okay? Think of it like the extracellular matrix of its connective tissue. Okay, so interstitial fluid is just the fluid within that interstitial space. It begins to build up because of this filtration process that occurs within capillaries. If we were to measure, in fact, the amount of interstitial fluid that's formed throughout the body, where we'd have to calculate the amount of interstitial fluid formed at each capillary bed, okay, and we'd have to add it up over a 24-hour period, it turns out that most of us generate between 2 and 3 liters of interstitial fluid a day. But earlier I said that that interstitial fluid is mobilized, it's removed, it's returned to the bloodstream. Yes?
So, do the workout people who like do this